Motion compensation is an algorithmic technique used to predict a frame in a video, given the previous and/or future frames by accounting for motion of the camera and/or objects in the video. It is employed in the encoding of video data for video compression, for example in the generation of MPEG-2 files. Motion compensation describes a picture in terms of the transformation of a reference picture to the current picture. The reference picture may be previous in time or even from the future. When images can be accurately synthesized from previously transmitted stored images, the compression efficiency can be improved. How it works: motion compensation exploits the fact that, often, for many frames of a movie, the only difference between one frame and another is the result of either the camera moving or an object in the frame moving. In reference to a video file, this means much of the information that represents one frame will be the same as the information used in the next frame. Using motion compensation, a video stream will contain some full frames. Then the only information stored for the frames in between would be the information needed to transform the previous frame into the next frame. Illustrated example: the following is a simplistic illustrated explanation of how motion compensation works. Two successive frames were captured from the movie Elephant's Dream. As can be seen from the images, the bottom difference between two frames contains significantly less detail than the prior images, and thus compresses much better than the rest. Thus the information that is required to encode compensated frame will be much smaller than with the difference frame. This also means that it is also possible to encode the information using difference image at a cost of less compression efficiency but by saving coding complexity without motion compensated coding. As a matter of fact, that motion compensated coding occupies more than 90% of encoding complexity. Motion compensation in MPEG: in MPEG, images are predicted from previous frames or bidirectionally from previous and future frames. B frames are more complex because the image sequence must be transmitted stored out of order so that the future frame is available to generate the B frames. After predicting frames using motion compensation, the coder finds the error which is then compressed and transmitted. Global motion compensation: in global motion compensation, the motion model basically reflects camera motions such as dolly, moving the camera forward or backward, track, moving the camera left or right, boom, moving the camera up or down, pan, rotating the camera around its y-axis, moving the view left or right, tilt, rotating the camera around its x-axis, moving the view up or down, roll, rotating the camera around the view axis. It works best for still scenes without moving objects. There are several advantages of global motion compensation. It models the dominant motion usually found in video sequences with just a few parameters. The share and bit rate of these parameters is negligible. It does not partition the frames. This avoids artifacts at partition borders. A straight line of pixels with equal spatial positions in the frame corresponds to a continuously moving point in the real scene. Other MC schemes introduce discontinuities in the time direction. MPEG-4 ASP supports GMC with 3 reference points, although some implementations can only make use of one. A single reference point only allows for translational motion, which for its relatively large performance cost provides little advantage over block-based motion compensation. Moving objects within a frame are not sufficiently represented by global motion compensation. Thus, local motion estimation is also needed. Block motion compensation: in block motion compensation, the frames are partitioned in blocks of pixels. Each block is predicted from a block of equal size in the reference frame. The blocks are not transformed in any way apart from being shifted to the position of the predicted block. This shift is represented by a motion vector. To exploit the redundancy between neighboring block vectors, it is common to encode only the difference between the current and previous motion vector in the bit stream. The result of this differencing process is mathematically equivalent to a global motion compensation capable of panning. Further down the encoding pipeline, an entropy coder will take advantage of the resulting statistical distribution of the motion vectors around the zero vector to reduce the output size. It is possible to shift a block by a non-integer number of pixels, which is called subpixel precision. The in-between pixels are generated by interpolating neighboring pixels. Commonly, half-pixel or quarter-pixel precision is used. The computational expense of subpixel precision is much higher due to the extra processing required for interpolation and on the encoder side, a much greater number of potential source blocks to be evaluated. The main disadvantage of block motion compensation is that it introduces discontinuities at the block borders. These artifacts appear in the form of sharp horizontal and vertical edges which are easily spotted by the human eye and produce false edges and ringing effects due to quantization of coefficients of the Fourier-related transform used for transform coding of the residual frames. Block motion compensation divides up the current frame into non-overlapping blocks, and the motion compensation vector tells where those blocks come from. The source blocks typically overlap in the source frame. Some video compression algorithms assemble the current frame out of pieces of several different previously transmitted frames. Frames can also be predicted from future frames. The future frames then need to be encoded before the predicted frames and thus, the encoding order does not necessarily match the real frame order. Such frames are usually predicted from two directions, that is from the ILP frames that immediately precede or follow the predicted frame. These bidirectionally predicted frames are called B-frames. A coding scheme could, for instance, be IBBPBBPBBPBB. Further, the use of triangular tiles has also been proposed for motion compensation. Under this scheme, the frame is tiled with triangles, and the next frame is generated by performing an affine transformation on these triangles. Only the affine transformations are recorded transmitted. This is capable of dealing with zooming, rotation, translation etc. Variable block size motion compensation. Variable block size motion compensation is the use of BMC with the ability for the encoder to dynamically select the size of the blocks. When coding video, the use of larger blocks can reduce the number of bits needed to represent the motion vectors, while the use of smaller blocks can result in a smaller amount of prediction residual information to encode. Older designs such as H261 and MPEG-1 video typically use a fixed block size, while newer ones such as H263, MPEG-4 PAR2, H264/MPEG-4 AVC, and VC1 give the encoder the ability to dynamically choose what block size will be used to represent the motion. Overlapped block motion compensation. Overlapped block motion compensation is a good solution to these problems because it not only increases prediction accuracy but also avoids blocking artifacts. When using OBMC, blocks are typically twice as big in each dimension and overlap quadrant-wise with all 8 neighboring blocks. Thus, each pixel belongs to 4 blocks. In such a scheme, there are 4 predictions for each pixel which are summed up to a weighted mean. For this purpose, blocks are associated with a window function that has the property that the sum of 4 overlapped windows is equal to 1 everywhere. Studies of methods for reducing the complexity of OBMC have shown that the contribution to the window function is smallest for the diagonally adjacent block. Reducing the weight for this contribution to 0 and increasing the other weights by an equal amount leads to a substantial reduction in complexity without a large penalty in quality. In such a scheme, each pixel then belongs to 3 blocks rather than 4, and rather than using 8 neighboring blocks, only 4 are used for each block to be compensated. Such a scheme is found in the H263 Annex F Advanced Prediction Mode. Quarter-pixel and half-pixel motion compensation. In motion compensation, quarter or half samples are actually interpolated subsamples caused by fractional motion vectors. Based on the vectors and full samples, the subsamples can be calculated by using bicubical bilinear 2D filtering. See subclause 8.4.2.2 Fractional sample interpolation process of the H264 standard. 3D image coding techniques. Motion compensation is utilized in stereoscopic video coding. In video, time is often considered as the third dimension. Still image coding techniques can be expanded to an extra dimension. JPEG 2000 uses wavelets, and these can also be used to encode motion without gaps between blocks in an adaptive way. Fractional pixel affine transformations lead to bleeding between adjacent pixels. If no higher internal resolution is used, the delta images mostly fight against the image smearing out. The delta image can also be encoded as wavelets, so that the borders of the adaptive blocks match. 2D plus delta encoding techniques utilize H.264 and MPEG2 compatible coding and can use motion compensation to compress between stereoscopic images. See also, motion estimation, image stabilization, interframe, HDTV blur, television standards conversion, vidfire, X-video motion compensation. Applications: video compression, change of frame rate for playback of 24 frames per second movies on 60 Hz LCDs or 100 Hz interlaced cathode ray tubes. References: Garnham, N.W., Motion Compensated Video Coding, University of Nottingham PhD thesis, October 1995, OCLC 59633188. External links: Temporal rate conversion, article giving an overview of motion compensation techniques. A new FFT architecture and chip design for motion compensation based on phase correlation. DCT and DFT coefficients are related by simple factors, DCT better than DFT also for video. John Wiseman, An Introduction to MPEG Video Compression, DCT and Motion Compensation, Compatibility between DCT, motion compensation and other methods.